Hello, hello everyone. Good morning. Welcome to our SUR seminar this week. Today it's a great honor to have Dr. Manish Bansal from Department of Industry and System Engineering at Virginia Tech join us to give the presentation. Dr. Bansal is an assistant professor at Virginia Tech. He received his bachelor's in electrical engineering from National Institute of Technology in India. He received his master and PhD degree from Department of Industry and Systems Engineering and Texas A&M. And he also spent several years at Northwestern University for the postdoc research. His research is focused on the theory of stochastic mixed integer programming, distributional robust optimization, location science, and their applications in production planning, telerobotics, and network design. His research has been well funded by NSF and DoD grants. Manish is also the vice president and president-elect of the Junior Faculty Interest Group of Informs. He has received several research awards that includes ICTAS Junior Faculty Award at Virginia Tech, Best Paper Award, Best Poster Award at MIP workshop, and second place in the Informs Interactive Session Poster Competition. So today, he will be presenting cut generation approaches for mixed integer program and two-stage stochastic programs. Thank you very much for joining us, Manish.
Thank you, Ran. I really appreciate your kind introduction, and thank you very much for inviting me. So, like Ran mentioned, so today I will present first a consolidated cut generating procedure for deterministic mixed integer program, and then I will introduce some application of cutting planes in efficiently solving two-stage stochastic mixed integer program. So before we proceed, let me just build some basic background. So as we all know about the mixed integer programs, so a mixed integer program is a mathematical optimization formulation which has some integer variables, some continuous variable, and objective function, and a set of constraints. It's a wide variety of the problems ranging from production planning to bioinformatics can be formulated as mixed integer programs or MIPs. A linear programming relaxation of a mixed integer program is essentially a linear program which has same objective function, same set of constraint, except that the integrality restriction on all the integer variable has now been relaxed. And an integer or a pure integer program is an integer program which has only integer variables. So here is this example of the LP relaxed region for an integer program with two integer variables, x1 and x2. Now let's say this region within this red boundary is representing the convex hull of the set of integer solution to this integer program. Now, in general, mixed integer programs are NP hard, primarily because given an integer programming or a mixed integer programming formulation, we only know about this black boundary or the LP relaxed region, and we do not know about all these red boundaries. So therefore, it is crucial to develop some inequalities called as cuts, which can reduce this gap between this LP relaxed boundaries and the mixed integer programming solution space. Or we would like to have strongest cuts, that is these hyperplanes, which are lines in this two dimension corresponding to these red boundaries and also referred to as facets. These cuts are essentially used in branch and bound algorithm to achieve better bounds and hence resulting in an efficient algorithm to solve mixed integer programs, which is called as we all know about the branch and cut approach. Now the question is how to develop these cuts. So let's see one approach. So here is a problem I have, which has a linear objective function with a set of constraints, and x are non-negative integer variable, and z is a non-negative continuous, is a set of non-negative continuous variable. So the approach is we form a relaxation using aggregation of these constraints and then create cuts for those aggregation. Now there are two ways to generate these aggregation. One is I aggregate all these cuts into a single constraint and obtain so-called single constraint relaxation. Or other is I can pick different subsets of the existing defining constraints and aggregate the constraint in each of those subsets and obtain this multi-constraint relaxation. So what's the significance is because since the original feasible set is a subset of the feasible set of the relaxation, which means every feasible point which satisfy the original constraint will also satisfy the constraints in the relaxation set, because all we are doing is just aggregating those constraints. Therefore, a valid inequality or a cut for the relaxation is also valid for the original problem. Okay, so mixed integer programming is one such fundamental procedure which is used to generate cutting planes for single constraint relaxation. And it utilizes this simple mixed integer set which has one unrestricted integer variable y and a non-negative continuous variable s, and with only one constraint alpha y plus s greater than or equal to beta. So this, and that's why you can see this is a simple set because you have only one constraint. So let's see how this will look like graphically. So here, this set, so in this axis, I have y, on this axis, I have s. So this set essentially is represented by these blue lines. And if I take the LP relaxation of this set, which means if I relax the integrality restriction on y integer variable, then I will get this gray region. Now, if I'm interested in the convex hull of these blue lines, then what is missing? Okay, so what is missing is there need to be one more constraint which is joining these 2 points. So essentially, if I add this constraint, then I will be able to obtain the convex hull of these blue lines. And how can I define this constraint? So if you observe, this is the single hyperplane I have. So the intercept on the y-axis is beta by alpha 1. And this point is corresponding to ceiling of beta by alpha 1. And this below point is the floor of beta by alpha 1. And this point up here belongs to alpha y1 plus s equal to beta. So I can obtain this point. So pretty much I have these 2 points known. Now, as we all know from basic high school math, if I know 2 points, I can very easily find the equation for the line or the hyperplane in this case. Great. So once I obtain this, and this is known as the well-known mixed integer rounding facet for this simple mixed integer set. What's the significance of this? Okay, so our goal was we were trying to see how can I obtain these cuts for this single constraint relaxation where I have aggregated all the original constraint into this single constraint. And here, just to remind, xj are my non-negative integer variable and zj are my non-negative continuous variable. So first what I will do is and this is a procedure from Nemauser and Woolsey back in 1990. And first I will do is, is to play with the coefficients in this constraint. Essentially, since zj is greater than or equal to 0, so I replace this e hat j or the coefficient of zj by max of e hat j 0 and times zj. So this will always be greater than e hat j zj. So I can have this inequality. Now I will just partition the set, which is 1 to n1, into j0 and j1. So I'm just partitioning the set 1 to n1 into j0 and j1 and just writing a hat j, summation of a hat j in this form. Now for all the elements j in j0, I will further replace a hat j with a coefficient which is greater than a hat j, which here I'm considering alpha 1 times ceiling of a hat j divided by alpha 1. So if alpha 1 is 1, then this is just the ceiling or the round up of a hat j. And for all the a hat j, where j is in j1, I'm just replacing this a hat j with alpha 1 times the floor of a hat j by alpha 1 plus the remainder of I will obtain corresponding to alpha 1, which I will be denoting by a hat superscript 1. So the whole purpose, if it's not clear, that's fine, but the whole purpose is why I want to write the original constraint in this form. So this is still a valid constraint to the original problem. So why I want to write it? Because I want to have all these expressions which are connected with alpha1 taken together so that I can write it in this form. So that's the whole purpose, that I have alpha1 times this integer expression plus up here I have this non-negative continuous expression. Why I want to do this? Now you might be able to relate it to when I introduce this simple mixed integer set, is because now I can substitute this integer expression by a single integer variable y and this non-negative continuous expression with a single continuous variable, non-negative continuous variable s. And since I know how to obtain a facet for a set which is defined by these two integer variables, I can just substitute y and s from the previous equations, and I will generate this cut, which is known as the mixed integer rounding inequality derived by Nemhauser and Woolsey long time ago. And prior to that, if here you set alpha1 equal to 1, then what you will get is the Gomery mixed integer cut. So which is like the very beginning of the cutting plane procedure. Okay, so what's the significance? So the significance is the mixed integer rounding inequality up here. It was later on observed that various inequalities derived for the problems, say lot sizing or the production planning, facility location, or the network design problem, the inequalities independently derived for these problems can also be derived by using this cut generation procedure. So which means now, why to just stay focused only on a single constraint set with only one integer variable? How about I prefer to go with a set which has m constraints, where each constraint has n integer variable y's, and it also has its some continuous variable vi associated to that constraint, and a continuous variable s which is common among all those constraints. So essentially here, if I set n equal to 1, m equal to 1, and vi equal to 0, I will get the simple mixed integer set that I introduced in the previous slides. So over past 30 years, a lot of has been done in considering various special cases of this set QMN. And today, I will discuss about how to generate the facets for this set QMN, which I will be calling as continuous multi-mixing set. And the procedure to generate cuts will be referred to as continuous multi-mixing cut generating procedure. And again, the significance is because if you see for the problems in this table, for all these problems on this column, the various inequalities derived in the literature can also be developed by using the continuous multi-mixing cut generation procedure that I will discuss. So like I mentioned, so here is the continuous multi-mixing set, which I'm denoting by QMN, where m denotes the number of constraints and n denotes the number of integer variable in each constraint. And here I will assume that the coefficients satisfy some so-called n-step MIR condition. And these set arise as a substructure in problems such as multi-capacitated lot sizing, multi-capacitated facility location, and network design problem. So here is this n-step MIR condition, but we won't get into the details of it. But if alpha1 so on to alpha n, which are these coefficients up here, are divisible, then these conditions are automatically satisfied. And there's another notation that I will be using is the beta superscript t. So I will, beta superscript 0 is essentially beta. So beta superscript 1 is the remainder of beta with respect to alpha 1. Beta superscript 2 is remainder of beta superscript 1 with respect to alpha 2, and so on. Okay, so in order to construct or in order to develop valid inequalities or the facets for this set, when we've studied this set with m equal to 1, and which is with n equal to 1, and here we will be generalizing his result. So we consider this a complete directed graph G with m nodes, where node 0 correspond to s greater than equal to 0, and each node in this graph correspond to a constraint in the set QMN, which means the node I correspond to constraint I in the set QMN. And we also associate a linear function psi n prime ij with each arc ij of this graph G, which in its compact form is written like this. We don't have to get into the details, but it's a compact form because it has this integer valued function, and it also has this recursive remainder function up here. But the result is much more simpler than what the result is saying we have is, if I pick an elementary cycle C, then this so-called n prime step cycle inequality associated with that cycle C, which is obtained by summing the expression psi n prime ij associated to each arc belonging to the cycle C and setting this expression greater than or equal to 0, is valid for the set QMN, and also define facets for the convex hull of the set QMN under certain conditions. Again, we won't get to the details, but why I call this as a consolidated cut generating procedure, because the cuts generating from this procedure subsume the mixed integer rounding cut that we discussed, mixed MIR, cycle, n-step MIR, and mixed n-step MIR inequalities that have been derived in the literature. For one example, if you have this continuous 2 mixing set with 3 rows, which is Q32, where you have 3 constraints, where each constraint has 2 integer variables, then if I want to derive facets for this set, all I have to do is I have to construct this complete directed graph with m plus 1, where m is 3, so you have 4 nodes, associate this psi function up here, which will be something, these nice linear functions up here. Now, if I consider the sum of these psi functions by considering the sum of these psi function associated to the arc in the cycle, which is, let's say I pick a cycle 0, 3, 3, 1, 1, 2, 2, 0. So this is a cycle I obtained from that graph. And if I sum this psi functions associated to that and set this greater than or equal to 0, it will give me a facet for this example. We have considered some other generalization of this set. So previously I said if it has some n-step MIR condition, but what if these conditions are relaxed? Then we have considered some of those, we have generalized the n-step cycle inequalities and have further generalized when some of the integer variable have some bounds, and we introduce a new class of inequalities called as the mingled n-step cycle inequality. And these inequalities subsume the continuous cover inequalities, cover and pack inequalities, 2-step mingling inequalities, n-step mingling inequalities, and n-step cycle inequality that I introduced before. Okay, so what's the significance of studying? So, like I mentioned, these inequalities, this cut generating procedure can be utilized to solve a variety of problems. So one such example is multi-capacitated lot sizing problem, and we will see how these cuts can be generated for this problem. So many of you might have studied about the lot sizing problem in the supply chain, and the problem is defined as follows. So let's say we have a retailer, and the retailer knows the demand over a planning horizon, which is for a time period, say 1 to t. And the constraint the retailer has is that he or she has to place an order, but there is only one truck with capacity C1 available for ordering in each time period. And the decision is to be made is how much should the retailer order in each time period, and such that the overall ordering cost and the holding costs are minimized. If we look at this in the manufacturing setting, essentially truck is replaced by machine, and the fixed costs, ordering costs are replaced by the setup cost. So if I look at the network flow representation of the problem, which means, and I'm doing the production planning and production and inventory planning. So which means that each node here is representing a time period. And in each time period, I know the demand denoted by, let's say in time period P, I know the demand is DP. I need to determine what should be the production in time period P, which is XP, what should be the inventory at the beginning of time period P, which is SP minus 1, and inventory at the end of time period P, which is SP. So this is a special case of network flow problem. So I can define the feasible region of this problem, which I will be denoting by X superscript CCLS. CCLS is the constant capacitated lot sizing problem. What does that imply is that in addition to the flow balance constraint, I have this additional constraint, which means that XP is less than or equal to C1 times Z1P, which means that the production capacity in time period P is C1. So if Z1P is 0, then I won't produce anything. If Z1P is 1, then I can produce at most C1. Now here, this is a constant capacitated, which means in each time period, I have a machine or a truck with same capacity C1. What if I have multiple machines of capacity C1, C2, so on, Cn, or I have multiple trucks with capacity C1, C2, so on, Cn. And I just want to decide which subset of those trucks or the machines are to be used in each time period so that I can satisfy my demand and ensure that I have the minimum production and the inventory cost. So this can leads to a generalization of the constant capacitated lot sizing problem, referred to as multi-capacitated lot sizing problem. And the only difference from the previous formulation is that now here the capacity constraints, in the capacity constraint, what you have is that XP is less than equal to the sum of binary multiple of n available capacity. So here I can consider either C1 or C1 plus C2 or C1 plus C2 plus C3 and or C2 plus C3. So all those different possible combination can be taken. So like I mentioned, the similar extension is in lot sizing in the supply chain. Instead of having a single truck with the capacity C1, now I have n different trucks with different capacity. And in each time period, I have to decide which subset of these trucks is to be used to procure my order from the warehouse. Okay, so again, so this is the feasible region of which is denoted by XMCLS, and I will be using MCLS to denote multi-capacitated lot sizing problem. So I want to generate some cuts for this problem, and a procedure is I've been talking about aggregation, so let's aggregate some of these flow balance constraints which are already in the equation form. So let's say I aggregate the constraints from P equal to K to some Mi minus 1. Again, I won't get into the details from where this Mi minus 1 is coming, but let's say I aggregate them from period P equal to K to Mi minus 1. What I will get is I will have Sk minus 1 plus submission of Xp from P goes from K to Mi minus 1. For now, let's forget about this part. And this will be greater than equal to. So essentially, I will have another constraint, which another variable up here, which I will consider as the slack and will reduce it to the equality form. So this will be greater than equal to the sum of the demand from K to Mi minus 1. Now, for all the time periods within the SI, I will utilize the capacity constraint up here and will replace them or get a relaxation by having this summation of CT times summation of ZTP. Now, if you observe up here, essentially, depending on how I'm selecting this MI, I can have multiple constraints. And this can have a form, which is, so I can select from K to M1 time period, K to M2 time period, K to M3 time period. So I'm doing this multi-constraint aggregation, which leaves me multiple constraint in the aggregated form. And this has the form, which is, I have this continuous variable S, which will be common among all those constraints. And then there is this VI, and I have this summation of alpha T, YIT, which means I have these n integer variables up here. So this relaxed form has the same structure as the continuous multi-mixing set, which means if I derive the cut for the continuous multi-mixing set, that can be utilized to derive the cut for the set XMCLS. So we did the same. We said, okay, let's derive them. And right now, only thing that is ensuring is just the validity of those cuts. We said, okay, let's computationally evaluate that. And we randomly generated some instances with 2 capacity modules and observed that with our cuts and the separation algorithm, and we added all those cuts at the root node and then let the Cplex solve the problem in comparison to without adding those cuts at the root node and letting Cplex to solve the problem. So by adding these cuts, we were able to reduce the integrality gap by 82%, and the number of nodes were reduced by 8.4 times. And the total time, which include the cut generation time, was reduced by 8.5 times. But if you hear, so from this, we observed that these cuts are strong. So that led me to think about, okay, can we say that, if these are strong, are they representing the facets for these capacitated problems? And that led me to obtain some facet defining or the conditions under which this inequality will be facet defining for the problems, where we call it as the single module, where instead of considering that you have the variable to be binary, it can be integer, which means that in each time period, you can have multiple trucks of the same capacity. And I studied some of the facet defining properties for some of the well-known KLSI inequalities, mixed KLSI inequalities, and sequential paired inequalities studied in the literature for this single capacitated lot sizing problem or the constant capacitated lot sizing problem, and also obtain the facet defining properties for the problem for the n-step mixed KLSI inequalities as well. And we observed that under certain conditions, these are not just strong cuts, they are also facet defining. And remember that all these cuts are special cases of the cuts that we will obtain using, the continuous multi-mixing cut generation procedure. So while working in this direction, we started looking at the problem and we said, okay, let's, instead of just looking at the feasible region, let's look at the problem in the holistic sense, which means let's also incorporate the objective function. And let's say now the objective function has this production cost, and which is represented by P bar T, and it has the holding cost function, which is represented by HT, and they are both concave. And the feasible region is still the same, which is X MCLS. And I still have those n capacities, and I also have the setup costs associated with these n capacities, which are constant. Okay, so, and in addition, we said, let's add subcontracting option as well, which means that in each time period T, I can also have an option to subcontract. But there is a cost associated with subcontracting, which is GP. If I subcontract rho T in time period T, then I have to pay GT of rho T, where GT is a concave subcontracting function. And we realized that if in this problem, when we set n equal to 1, this was studied by Atomtuk and Hogbaum back in 2001. And they provided they provided a nice algorithm to solve the problem for n equal to 1. So me and my PhD student, we said, okay, let's see how we can generalize this for n greater than equal to 2. While doing that, we realized that the problem can also be the problem MCLS with subcontracting, which I'm denoting it by MCLSS, can also be reformulated. And the way to reformulate is you can get rid of these capacity constraint if instead of considering the concave production cost, you consider piecewise concave production costs with, let's say, M breakpoints. And which is nice. So we refer to this problem as lots. So this problem has already been studied in the literature. It's referred as the lot sizing problem with piecewise concave production cost, and was studied by Kosha and others. So we said, okay, let's understand this problem and the algorithm, and we developed a new exact algorithm which is computationally faster. I won't get into this algorithm, but even after having this algorithm for the lot sizing problem with piecewise concave production cost, the issue was that the number of the breakpoints are exponential because each breakpoint belongs to this set where you have to consider all possible non-empty subsets of 1 to n. And as a result, so although Atomtuk and Hogbaum provided this, solve this problem MCLS with n equal to 1 in OT5 time, and you can solve this reformulation in OT2m plus 3 time, where m is the number of breakpoints. But the number of the breakpoints when you do the reformulation, it's because of this structure we have with the n capacities, the worst possible number of the breakpoints in the reformulation will be 2 to the power n minus 1, because I have to consider all possible subsets of 1 to n except the empty set. And if I do that, then what will happen? So if I just want to use this reformulation for this problem. So the complexity for the problem with n equal to 4 will lead to, in worst case, 15 breakpoints and will lead to order of t to the power 33 algorithm. And in general, it will be t to the power 2 to the power n plus 1 plus 1. But we introduce a new algorithm which is specific to MCLSS, and we refer to it as a fixed, it belongs to the class of fixed parameter tractable algorithm, which means that if I have a fixed n, then the problem is polynomially solvable. And this algorithm is, so now if you can compare the complexity between these two algorithms, between reformulating it and solving it using this new algorithm, essentially for n equal to 10, instead of having t to the power 2049, you have t to the power 23. This paper is available on Optimization Online. So I would get to the details of like the algorithm, but because of it, it is working computationally very efficient. And it is also, another thing is what this resolve is that for a fixed n, the problem MCLSS can be solved in polynomial time. Okay, so all along when I was discussing about the lot sizing problem, I was assuming that the demand in each time period is known. But what if I don't have the complete information about the demand? What if for the initial k time period, I know the demand, but for the remaining time periods, I do not have the exact information about the demand. What I have is that there could be 3 different possible scenarios, which is, and with some probabilities P1, P2, and P3. And I need to decide the production in the initial time periods and the inventory at the end of time period K, so that when any of these scenarios will be realized, the overall production and the inventory cost is minimized. So this problem is called two-stage stochastic programming because it has 2 stages of decision making. The first stage is here and now decision. That is, we decide the production and inventory for first K periods. And the second stage is wait and see decision making, where we decide the production and inventory for the remaining periods after the realization of demand. So this takes us to the world of optimization under uncertainty. And in more general setting, a two-stage stochastic program is defined as follows. So like previously we said, so now here we have this deterministic linear program where all the data parameters are known. But what if some of the data, which is let's say G, matrix T, WR, are uncertain? So what you can do is you can describe this uncertain data by a random variable. And let's say assume that you know the probability distribution corresponding to it, and you also have the sample space associated to this random variable. Like I mentioned, this problem is a 2-stage of decision making because you make some decision here and now, which is you decide how much to procure in stage 1. And once the uncertainty is realized, you make your decision of how much to produce in the second stage. And here the omega will denote the index to a specific data scenario, which belong to the sample space, big omega. And each data element or the parameter that varies with the scenario is identified by superscript omega. So in order to tackle this problem with finite sample space, this is a well-known recourse model from the Denzing, where he introduced these y omega variables corresponding to each scenario and rewrote this problem where you have the finite sample space as this large-scale linear program, where in the objective function, this expectation is replaced by the submission function up here. Now, interesting thing about this model is that it has a nice block angular structure, because here you see this first stage integer variable, the first stage variables are appearing here, and the second stage variables are y omega are not connected to each other. So before I go to the decomposition, essentially this problem can also be considered when you have the mixed binary or the mixed integer first stage and the second stage variables. So this problem can be nicely decomposed where you have this first stage problem, and in the first stage you have these here and now variable x, you have this function q, which is referred to as the recourse function, and for each scenario omega, this recourse function is defined by this mixed integer program, and it's a parametric mixed integer program because here x is an argument up here, and this is referred to as a second stage subproblem. Now, one of the concern or the challenge in solving these two-stage stochastic mixed integer programs, which I will denote by TSS MIP, is to optimize this NP-hard second stage problem for a given first stage decision and a particular realization or scenario of the uncertain parameters. So essentially, not just you have to solve this for each scenario, you also have to solve it for each x, right? If you are working in the algorithmic fashion. So question is, can we obtain some tight formulation or the linear programming equivalent for the second stage subproblems by adding some globally valid cuts? When I say globally valid, because I can obtain the convex hull of this set for a given x, but if I add those cuts, will those cuts be valid for some other x? So I need to make sure that they are globally valid, which means they're valid for each x. If we will succeed to do that, so if you have a problem with 31 first stage integer variable, 30 second stage integer variable, and with 1,000 scenarios, essentially overall problem has 300,031 integer variable. But if I can obtain this linear programming equivalent for the second stage, I can reduce this number of integer variable to 31. And I can also be able to reduce this recourse function, which is a lower semi-continuous function in the presence of integer variable, to a convex function in X. So, so there's a wide variety of the literature where essentially the first stage has been considered to be pure integer variable, and the second stage is a mixed integer program. There are very few where the mixed integer variable have been considered in the first stage. So we decided to stay focused only at the case where the first stage has only pure integer variables. And we introduced, we studied some two-stage stochastic mixed integer programs with some structured mixed integer programs in the second stage, and try to obtain the convex hull for the second stage problems. And here is this just one example I'm sharing. And if so, in the first stage, I have pure integer variables, and I have this recourse function q omega x, where the constraints are where you have three types of variables. One is y1 omega. So you have n integer y1 omega variable. You have y2 omega, which is you have this continuous variable, which is corresponding to that particular constraint because you have this identity associated to it. And you have this y3 omega, which is a single non-negative continuous variable, which is connecting all the constraints, or which is common among all the constraints. So it has to be like 1 times this. So we now here this w omega, we demonstrate that if w omega is a unimodular matrix, then by adding some order of m square linear constraints and some order of m continuous variable, we can obtain a tight extended formulation for this set, and hence we can relax the integrality restriction on y1 omega variables. And if you notice, you can connect it that this is related to, it's a special case of the continuous multimixing set. More details and more such examples are provided in this paper. Now, recently, me and one of my students, we said, okay, let's further generalize two-stage stochastic mixed integer program by considering this LP norm in the objective function. And we said, okay, let's further extend it by considering this weighted sum of LP norms, where each norm has a different set of integer variables, y, j, omega, and these integer variables are connected by these linear constraint up here. And we assume that without loss of generality, this matrix fj omega and t omega are integral. And said, okay, let's see, can we do something with this type of problem? To understand this, we said, so one special case of this will be when you have two-stage stochastic quadratic integer program. because this is where you have the quadratic objective function. And we said, let's see if we consider only some structures where EJ omega and W omega are network flow matrices, or EJ omega is a totally unimodular matrix, or W omega are identity or zero matrix, and see how can we obtain this continuous programming or the convex equivalent for this conic mixed integer program in the second stage. And we went back to the literature for the deterministic conic mixed integer set, and we observed that Atom took and Narayanan, they studied the obtained this convex hull of this simple polyhedral conic set, which has only one polyhedral constraint, and which has only one unrestricted integer variable sigma, and a continuous variable, a non-negative continuous variable rho1. And they introduced the so-called conic MIR, conic mixed integer rounding inequalities, to obtain the convex hull of this set. And we said, okay, let's see, can we have some multi-constraint generalization of this? So I'm denoting this set by S11. So can we have some multi-constraint generalization of this set, where you have M constraint, where each constraint has one integer variable, which is common among all of them, and it has its own continuous variable as well. Or we further generalize it to the n integer case, and consider this most generalized form, where you take this set Sm and K, which is the intersection of this n integer multi-constraint generalization, along with some linear constraint A sigma greater than or equal to B. And we obtained this set, and we said, let's see what we can do. And what we observed was, or what we proved was, that under some of these conditions, where, for example, if A and this matrix GK are network flow matrices, then just by adding the conic mixed integer rounding inequality for each defining conic inequality of the set, we can obtain the convex hull of this set. If we can do that, then we utilize it to obtain a convex hull, or the convex approximation of this recourse function, where you have W omega is a network flow matrix, and EJ omega is also a network flow matrix. Again, the significance of this was more on the computational side, like I mentioned. So when we were considering the two-stage stochastic mixed integer programming instances, Cplex was not able to solve 248 out of 384 instances within a time limit of 10 hours. However, after adding those cuts, we were able to solve the problem in 19 minutes. And similarly, for the two-stage stochastic conic mixed integer program with p equal to 1, Cplex is not able to solve the problem in 800 seconds, but after adding the cuts, we are able to solve it in 143 seconds. So which reduced the time by up to 25 times and 4.6 times in average. So just to give you a glimpse, I won't get into the details, but here, these are some of the instances we generated. And if you see that these columns up here are without cuts, and this is with cut. If you observe the number of integer variable, and so this is the problem which has 5 first stage integer variable, 10 second stage integer variable, and these are the number of the scenarios. So if you see, as the number of scenarios is increasing, so the number of integer variable in the problem is increasing rapidly. Now, if you're able to convexify the second stage problem, then essentially you can relax the integrality restriction on them. And this is the number of integer variable you will have after adding those cuts. Of course, you have to add these cuts as well. So there is a trade-off between relaxing the integrality restriction with adding more cuts. And if you see, the time taken has been drastically reduced by adding these cuts. All these instances are average over 5 randomly generated instances. Okay, so I don't have much time, but I'll in next 2 minutes I'll just discuss present some other generalization that I'm interested in of the two-stage stochastic mixed integer programs. So here is this two-stage stochastic mixed binary program, where the first stage has pure binary variable and the second stage has mixed binary variables. Now here I was assuming that the probability distribution corresponding to this random variable is known. But what if the distribution is not known, and this distribution belongs to some set ambiguity set P, which can be defined by bounds on the moments or the bounds on the variances, or you could have a reference probability distribution and you're looking for all the distributions which are at epsilon distance from them, which leads to the Wasserstein's metric. So the significance of this generalization is it provides the ability to allow incomplete information on probability distribution, and it also provides adjustable level of risk aversion, which means that I can have the set P to be defined for all probabilities supported on omega to get the robust optimization, and I can have this fractured P to be a singleton set, which leads me to two-stage stochastic mixed binary program. We have recently also studied a further generalization where we said, okay, let's add some of these disjunctive constraints in both the first stage and the second stage. By disjunction, it means that the feasible region will belong to either a polyhedral set defined by one disjunction or the other, or one element in the disjunction or the other. And one such example of this is a toy problem up here. So you have these disjunctions. So the feasible solution can either satisfy this constraint or this constraint. And similarly, in the second stage, you have the second stage feasible solution can either satisfy this constraint or this constraint, and all of them have to satisfy this constraint 7b. Interesting thing is, if you see the second stage problem, so the second stage problem is non-convex, and also, though we know about how to tackle these disjunctions using the Balas's result, but here these disjunctive sets or the feasible region is changing as we are changing x. Okay, so with the change in x, so if I see this is for omega equal to omega 3, and for different x, I'm getting a different second stage feasible region. So if I obtain the convex hull of this set, that will not work for this, because it will in fact cut off the region of this A. So closely related literature is definitely for the inspiration is this biography of Egon Balas and all his work, and the literature in two-stage stochastic mixed binary programs, and also we looked at the literature in two-stage distributionally robust linear programs, and there we observed that most of the work was related to the reformulating the problems and then solving them. So we introduced some generalization of the existing methods. So there is an L-shaped method for two-stage stochastic linear program. So we introduced a distributionally robust L-shaped method for two-stage distributionally robust linear program, and thereafter extended it to distributionally robust integer L-shaped method by utilizing some parametric cutting planes. And to solve the two-stage distributionally robust disjunctive program, we utilize the Balas's linear programming equivalent, but it is more like now parameterized by X, and also his sequential convexification approach for the disjunctive program. We demonstrate that under certain condition and for a family of ambiguity set, these algorithms are finitely convergent. And we also consider some computational results for the distribution robust version of instances from stochastic integer programming library. So in conclusion, so this was just a slide my student obtained from Dimitri Bertsima's presentation for Gurobi, and this is the progress for mixed integer programming optimization. And it said like there's a speed up of the CPLEX from 1991 to CPLEX 11 in 2007 has been 29,000 times, and thereafter Gurobi is comparable to CPLEX 11, and there's a speed up in Gurobi for another 48.7 times, and the total speed up is being calculated as, again, I haven't verified these numbers because I didn't know about CPLEX 1.2, but let's say the total speed up is the 1,400,000 times, and you can check there is a significant role played by cutting planes in solving the problems using these state-of-art solvers, and you can verify that by turning, whenever you solve a problem, you turn off the cuts or you turn on the cuts, and you can see the difference. So we know that cutting planes have played and are playing a very important role in speed up of mixed integer optimization. The conclusion is the cutting plane will play a crucial role in the speed up of stochastic and the distributional robust mixed integer optimization as well. So with this, I end my talk. Here are some of the references. And if you have any question, I'll be very happy to answer them. Thank you very much for your patience and listening to me.
Thank you very much, Manish, for the nice presentation. So we have about like 10 minutes remaining. So if we can open the floor for any questions. If anyone have any questions, we can please just turn on your audio and speak, and or you can type in the chat box. We can check the text there as well. Is there any question?
I have a quick question. Can you mention the size of the mixed integer programming instances you considered when you were comparing the computational time?
Let's see. So I don't have the table for, so these instances you're talking about?
Yes, next.
Yeah, so here, yeah, so these are for the two-stage stochastic conic mixed integer program with only polyhedral constraint. So here, if I look at the extensive formulation, which is like the large scale conic integer program, then it has this hash I variable is the number of integer variable. And these are the number of linear constraints in the problem. And so this is before you add any cut. So if we are talking about this problem with 5 integer variable in the first stage, 10 integer variable in the second stage with 50,000 scenarios, it has 6 million integer variables and 6.8 million linear constraints.
Got it. Thank you.
Thank you.
Is there any questions? We have some more time. Okay, I think if it's no more questions, I think that'll be the, let's wrap up. That'll be the end of the presentation. Thank you very much all for joining us today for this seminar presented by Dr. Manish Bansal. Thank you again. Let's give him an applause for giving the nice presentation.
Thank you, Ryan, and others for organizing the session.
Sure.
I really appreciate it.
Okay, thank you very much all for joining us today. Enjoy the rest of the day and have a good weekend.
Thank you.
Thank you, Sean.